Oh, it's not a big issue. I think we can upload the video later on. Okay.
Can you see my slides and can you see them move?
Yes.
Yeah.
You can see very well. That's good. Okay. So let's start. I hope that you are enjoying the summer school. So today it's a lighter day with only 2 practical talks. So it is now my pleasure to introduce you Graham Neubig. Graham is an associate professor at Carnegie Mellon University. His work focused on natural language processing, specifically multilingual models and natural language inference. Much of his work relies on machine learning with applications to NLP problems such as machine translation and natural language understanding. He published regularly in top venues in natural language processing, machine learning, speech, and his work won several awards at EMNLP, EACL, and NACO. So thank you very much again, Graham, and you can start whenever you want.
Okay, great, thanks. So thank you very much for the invitation. I'm happy to give the talk here today. This time I'm going to talk about how can we know what and when language models know, based on some work that I've done together with Zhengbao and Frank, 2 students in my lab, and Haibo and Jun, who are researchers at Bosch. If I have time, I might also talk a little bit about interpreting your evaluation, interpretable evaluation, and a software package called Explainaboard that we're making, but we'll see if there's time for that at the end. So basically, language modeling is the task of predicting the likelihood of a sentence, P of X, or the text. And there's, so if you get kind of a natural sentence, like Barack Obama served as the 44th president of the United States. Sorry about that. If you get Barack Obama served as 44th president of the United States, the probability of X would be high. However, if you get some sort of word salad like this, that's not natural English or any other language, then the probability would be low. But that's not the only thing that language models do. They do this sort of judgment of syntax, but in addition to that, they also can find things that are syntactically correct, but just implausible. They can talk about semantics. And also they have, ideally, if you have Barack Obama served as the 42nd president of the United States, that's not true. So ideally, they would also give a lower probability to this sort of factual mistake. And they can also talk about common sense. So Barack Obama reached a height of 50 feet tall. People generally don't reach a height of 50 feet tall, so we know that this is not true. So one of the interesting things is now we have large language models trained on lots of data. For example, one of the most famous ones right now is GPT-3. But basically, what we are able to do with these models is basically test the sort of knowledge that they encode in them. And there's different ways we can do this. So one example of this is we set up a kind of prompt like this that says Tokyo is the capital of blank, where we mask out a single word, and then we try to predict that word using the language model. And this essentially these are the actual predictions that you get from that. And you can see that it picked Japan with a very high probability. So you can see it essentially, this specifically was done using BERT, which I think a lot of people may be familiar with. And it can actually predict the correct answer. There's other things you can do with this. So you could also do something like text classification, where you write the text that you want to classify. So if it's "I loved this movie" is the text that you want to classify, then in the end you append something like "the movie was masked," and then depending on whether it picks bad, okay, or good, you could figure out the sentiment of the original text on the left. So this is a very versatile method. You can do lots of different things with it. And I'm not necessarily sure whether we really, want to use a language model as a tool to answer factual questions. But the reason why I'm so excited about kind of this direction of being able to prompt language models for knowledge is if you look at more complicated tasks where we can't actually easily build just a system to handle them, like let's say free-form dialogue. Nonetheless, there's a lot of knowledge that you would need to capture in these models in order to get this right. So this is just one example between a human user and Mina, a chatbot developed by Google. And what you can see is it says, hi there, how's it going? Da, 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 da. And then it says, the human user says, what is your favorite book? And Mina says, oh, that's a toughie. Right now, I'd have to say it's A Dance with Dragons, but Harry Potter is a close second. Oh, I love Harry Potter. I've read the series at least 5 times over. So, haha, same probably. Which one do you like the most? Probably Chamber of Secrets. So you can see there's a lot of factual knowledge in here that this chatbot is actually getting right, just because it was trained as a language model. Like the fact that Chamber of Secrets is a book in the Harry Potter series, or that Harry Potter is a series at all. But the issue with this is if you go back and look at the conversations, there's an equivalent number of conversations that kind of just get the facts completely wrong. So I still think that it's very interesting to kind of know the limits of our language models, what they know, what they don't know, and how then think about how they can be used in these contexts. So I'm going to talk about 2 different varieties of difficulty that we have when doing this sort of prompting. So language models were never trained to solve the exact kind of factual prediction tasks that we're asking them to solve, or text classification tasks that we're asking them to solve. Basically, they were trained to predict the probability of a text, and just as a byproduct, they're able to do this, text classification or factual knowledge prediction. And because of this, these models are very sensitive to the wording that we use to prompt them. So if you get the wording a little bit wrong, they might not answer a fact that they would have been able to do with a different wording. And another issue is that language models will basically predict an answer even when they have no idea whether the fact is correct or not. So in this talk, I'm going to talk about these 2 problems in turn. The first one is how can we know what language models know through better ways of prompting them for the knowledge contained in their parameters? And how can we know when language models know? And in order to do that, we're going to use a concept called calibration from machine learning, which I'll explain about later. So for the first research work that we did, I'm going to talk about how can we know what language models know. This is a paper that came out about a year ago. And if we look a little bit closer at a factual prompting problem, let's say we want to know the developer of DirectX. And so if we have the prompt on the left, DirectX is developed by Mask, then what we can see is that the model predicts Intel over Microsoft, which is not correct. However, if we change the prompt to Mask released the DirectX, DirectX is created by Mask, both of these give you the answer Microsoft, the correct answer instead. So you can see that it is actually pretty important to choose which way of prompting the models. So what we asked in this paper is how can we most effectively probe language models? And so the motivation for this is number one, any given prompt only provides a lower bound estimate for the level of accuracy that you could get by prompting a language model for knowledge. And what we would like to do is we'd like to get a tighter estimate by automatically discovering better prompts that we could use or combining together a diverse set of prompts. And the answer to this question is essentially yes. If we do careful prompt design, this leads up to an 8.5 increase in fact retrieval accuracy. And actually, as I'm going to talk about at the end, there's been quite a bit of follow-up work after this that does even better. So we examined two different varieties of ways of figuring out what kind of prompts are the best for like finding factual knowledge from language models. And the first one is essentially we go through a big corpus, a big text corpus, and try to find all pairs of entities. So in this particular case, we're talking about a factual query over relations over entities. So for example, where was Barack Obama born would be one question that we'd want to be answering. And so we go through a big corpus and it says Barack Obama was born in Hawaii. And because we have this pair of a head entity and a tail entity, we then extract the middle words, like X was born in Y. And so if we have lots of different pairs of like Barack Obama and then Hawaii and then some other celebrity and where they were born, we could extract a bunch of these patterns and take the most frequent ones or the most reliable ones in some way. And this is a pretty common method for extracting patterns for relation extraction. Then we also have a dependency-based method. And the dependency-based method, this also has been used in relation extraction before language model, before we used it for probing language models. But basically the idea is if we only take the middle word, we might miss some nice patterns based on the syntax of the sentence. So for example, if we have France is Paris, we would extract this word France is Paris, or we'd extract the pattern X is Y, which obviously isn't very good. So what we do instead is we do dependency parsing, which is basically a method of syntactically analyzing the sentence and finding relations between words. And then we take the shortest dependency path between the two words. So we have France of capital is and then Paris. So then we extract this pattern capital of X is Y. So both of these methods basically try to extract these prompts over a large corpus. Another thing that we tried is using paraphrasing. So basically, if we assume that we already have a set of human created prompts, like X shares a border with Y, what we do is we paraphrase it into a bunch of other types of prompts. And specifically what we did was we just translated into German and then from German back into English, but really, any method of paraphrasing would be equally reasonable to solve this problem. So another thing we tried was prompt ensembling. So the basic idea is that if we want to figure out the owned by relation for a particular head word, we might be able to extract different prompts either by different varieties of mining, or by mining several different middle words, or by paraphrasing or something like this. And what we do is we combine together these various prompts and we multiply each of the prompts by a weight corresponding to kind of how trustworthy the answers we acquire from that prompt are. And we set our final score as being basically this weighted average, weighted log probability of the tail entity Y given all of these prompts. Oh, I see a question. So thanks for the question. How are the weights chosen? The weights are basically, the weights are basically chosen by maximizing the weights to maximize the log probability of getting the correct answer. So we have some training data, and we try to maximize the probability of the training data. Okay. Yeah, thanks for the question. And if you have any questions, please just ask in the QA section or raise a hand or something. So for the experimental settings, what we did was we tried to apply these methods to a task of extracting subject-object pairs from 46 different relations from Wikidata. This was kind of the example that I gave before from Petroni et al., like Tokyo is the capital of Japan, Barack Obama was born in Hawaii, or DirectX was developed by Microsoft. And so we have all these pairs, each has 1,000, and for 46 different types of relations. There's also LAMA-UHN, which is a particularly difficult subset of facts from LAMA. So this was extracted by previous work. And basically, they're trying to get rid of the facts where kind of the surface form of the fact makes it very easy to guess. So like a particular person was born in France and their name is very French, makes it easy to extract this. There's also Google RE, which has three relations. So do we need training data associated with each relation, or can we generalize over relations based on other relations? So that's a very, very good question. So in the particular method we're using here, yes, we do need training data for each relation. It is possible that you might be able to get around that in some way, but I don't know of an easy way to avoid having at least some examples for other relations. I guess if you knew the name of the relation, you might be able to somehow turn that into a prompt or something, or bootstrap, or but yeah, very good question. Okay, so we did our main experiments on llamas, the 46 relation data set. And for our methods, we have prompts, which are either manually created. So these are the prompts that came with the llama dataset itself. We also did mining-based prompts from Wikipedia articles. So we tried to mine using the center words or the dependencies. And we also paraphrased prompts using round-trip translation. And for ensembling methods, we tried the top one, the best performing prompt for each relation selected on the training set. We also tried ensembling, so combining together 40 prompts by weights learned on the training set. And then we also did an oracle. And what the oracle does basically is if any of these 40 prompts get it correct, we judge it as correct. So basically what this is telling us is how well could we possibly expect to do if we had a very good ensembling method to pick out, the best prompt that we should be using. And in terms of metrics, we use accuracy, so the average accuracy across the different relations. So here are our results, and if we go through, we see mine plus manual, mine plus paraphrase, and manual plus paraphrase. And basically the red line here is just using the manual prompts. So blue is the top one prompt. And what we can see is that the top one prompt, specifically of the manual plus paraphrasing method, improves pretty significantly over the baseline. Even in the other cases, it improves over the baseline somewhat. And then we also ensembled them together. So we have mining plus manual, or manual plus paraphrase. This gives us many different prompts that we can ensemble together, and we see that that actually improves the accuracy by quite a bit. And if we look at the Oracle, we could see that there's even more headroom for improvement if we were better at picking these prompts. But long story short, the type of prompt that you use to query a language model is very important with respect to the accuracy, and you can combine together multiple prompts to get better accuracy as well. We also have the results on the LAMA-UHN corpus and the Google RE corpus, and both of these in general seem to be doing a bit better. And it's also interesting to look at the case studies of the individual prompts that we were able to generate. So on the left, we see manual prompts. X is affiliated with the Y religion. So this was created manually by a human who thought this would be a good prompt. However, we have X who converted to Y. And this ended up being a much, much better prompt. And the reason may be that this sort of phrase is much, much more common in Wikipedia. And so the language model is just better trained to appropriately put the person's religion in here. It's also kind of simpler, more concise. There's something in the middle instead of kind of around the edges. So this ended up being quite a bit better. See two questions. Why do I think that man plus para, I think probably man plus para? Or mine plus man, I guess. Why did this give a better accuracy? I think part of the reason why this gave a better accuracy, or Oracle accuracy and ensemble accuracy, is there's more diversity here. So if we have the man plus para ones, this means that we paraphrase the manual prompts. If we have the mine plus para ones, this means we paraphrase the mine prompts. So mine plus man is the only one that actually has two different varieties of original prompts. So yeah, good question. Are there any extra considerations to make for significance testing and reproducibility when using prompts to solve a task, e.g. providing all prompts? So in terms of significance testing, I think, unless I'm mistaken, I think you would just do normal significance tests over the like accuracy gains to make sure that the accuracy gains are real gains and not insignificant. That's a good question. I think we had that in the paper, but I'm not 100% sure. We didn't list it on the slide here. For reproducibility, I would definitely, release all of the prompts, and that's what we did for this paper. We released it in a data set called Alpaca, kind of a play on words for llama. That being said, there is some very interesting work recently that shows that it's not necessarily the case that, like, it's not easy to design prompts without kind of a lot of experimentation. It's a paper by Ethan Perez and Kyung-Hyun Cho and others. So there definitely are concerns about, the realness of the gains according to these methods. can we do data augmentation by rephrasing every time with manual prompts in pre-training? That's a really good question. I've not thought of that before, and I don't know of any work that has done that, but it seems like an interesting idea. So just to rephrase, to make sure I understand correctly, you would paraphrase some of your data during the training of the language model to make it more robust to lexical variations. Yeah, it seems like a good idea. How is the diversity of the prompts measured? We didn't really measure diversity of the prompts, if I remember correctly. Just kind of qualitatively, I guess. How to deal with ambiguities in the prompt questions in the cases where the prompt can have 2 or more correct responses? Oh, that's a great question. And in fact, many of the relations in here are actually one-to-many relations. So we did do 2 things to try to deal with this. Specifically, we created another follow-up data set that I'm not going to talk about called X Factor. It basically does this prompting multilingually. And in that case, we treated any permissible answer correctly, and also treated aliases of entities as correct. So if you had like Barack Obama and President Obama, or Hawaii in the state of Hawaii, any of the paraphrases would have been correct. If you're just talking about the ambiguity in the prompt itself, I think ideally the methods that we're proposing here for finding the ideal prompt would try to find a prompt that is kind of specific enough to get the answer correct, but not so specific that the language model has never seen it before. And I think also the prompt ensembling might be helping out with this as well. So you can get kind of like a less specific, some less specific questions that might be a little bit ambiguous, but then you can have more specific prompts to make it to rule out any wrong answers as well. More general question about language modeling. Why do all the larger models train on language modeling as a primary task and fine-tune to other tasks? Are there methods that are trained on other tasks and achieved good results on language modeling? So this is a really good question, and I think the answer basically boils down to the fact that language modeling has the least stringent data requirements of any task. So the language modeling just needs raw text, whereas most other tasks need something else. There's different ways that you can use a language model, and to kind of like split them up into 2 big categories that are most common right now. One way is to use the language model to solve a task directly. And in this particular presentation here, I'm taking this approach. Basically, we take the language model, we use the probabilities from the trained language model directly to try to answer factual queries. However, another method for using language models is to train the language model on the language modeling task, but then take its representations and use its representations to solve another task. So this is something like BERT or any other sort of contextualized representation method. In those particular cases, people have definitely seen big gains or big improvements by also training on other tasks that have a lot less data. So just to give one example, there's the natural language inference task, which is basically like deciding whether 2 sentences are, contradiction, entailment, or neutral. Try to figure out whether one sentence follows from the other. And training on that task, in addition to language modeling, has also proven to be quite like useful when using those features for downstream tasks for things like paraphrase identification or evaluation of machine translation output or other things like this. Yeah, so very good question. In terms of whether training on other data improves accuracy on the language modeling task itself, the task of predicting probabilities of sentences, that's a good question, and I can't immediately think of very strong examples of that, but it's certainly possible. It might help you generalize to new domains or other things like that. So good question. Okay, so I will move back to this. I have another question. Thank you for all the questions. These are great. Let me finish this slide and I'll get to that. One other thing is that we found that even simple edits can cause a really big change in accuracy. So just even plays in position, plays in Y position to plays at Y position caused a pretty large gain in accuracy. X was created, made in Y. So the question is, all these probing methods will help measure the goodness of the model, but can it also help understand what the model does not do well? So that's an excellent question, and that actually goes into the interpretable evaluation thing that I was hoping to talk about at the very end here. But basically, I think more or less, once you have a pretty good suite of probes for different types of things, like let's say you're not just probing factual knowledge, but you're also probing syntax or other things like this. The probes where the model does particularly well cause, are the things the model does well, obviously, and then if you flip it on the head, the probes where the model fails more often than not are examples of things that it does poorly. There's a natural follow-up question to that, which is how would you design a good suite of probes? And I think the answer for that is intuition or something more systematic. Maybe I'll have a chance to go into that at the end of the presentation if there's more time. Great. So yeah, thanks a lot. So the next thing I'd like to show is that we were able to probe other language models as well. So we tried 3 different language models, one being Neubig, BERT, and Ernie. So these are all just trained in different ways. Neubig and Ernie are trained specifically to try to capture more like knowledge from knowledge bases or information about entities. And we found that basically in all cases, this Ernie ended up being the best, and the relative utility of these prompt design methods across the different models was about the same. Interestingly and importantly, the results were somewhat consistent across 2 different models. So if we trained on BERT and then tested on BERT versus trained on the ensemble weights on Ernie and then tested on BERT, we could see that there was a little bit of a decrease when the prompts were trained on a different model, but it wasn't a huge decrease, and we still did better than if we weren't training these ensemble weights at all. So this shows that there is some sort of kind of generalizable pattern with respect to the prompts being good on one language model. How do I explain the difference between Neubig and the other 2? To be honest, I think it's probably just that, it was trained on less data, or not trained in a way conducive to answering these queries. But this was not something we looked into super carefully, so I don't have a really strong answer with respect to that. Okay, so I talked about our work now, and actually, since we've done this work, there's been quite a bit of follow-up work on designing prompts. And in fact, there's so many that it's kind of hard to summarize all of them in a presentation. But I'm going to talk about two other ones that I think are kind of particularly worth mentioning. So the first one is AutoPrompt, and AutoPrompt basically is a method where you take the original input and you get a template, and you append the sentence, and then you have like basically 5 spaces for trigger tokens that you could add in here, and then you have the final basically slot for where you're going to predict the answer. And what AutoPrompt does is it basically does a gradient-based optimization method to try to find the ideal words to put in these trigger slots to maximize your accuracy. And so basically it says a real joy, and then you get these kind of like not understandable words: CLN, atmosphere, a lot, dialogue, clone, totally. And in the end, it predicts some words, and then you add them together to get positive or negative. You add the probability of the words to get positive or negative. So noticeably, unlike our method, where we kind of made an attempt to keep the prompts being, human readable things, here it's just doing optimization and getting basically something not very meaningful, but nonetheless good at improving your accuracy. And then if you take this even a step further, there's this method of prefix tuning, where basically instead of having a prompt that consists of real words, they just optimize the vectors of the prefix, the continuous vectors of the prefix, like directly. So you learn some embeddings for each input and each layer of the language model. And this is very easy to optimize, because basically all you need to do is you need to fix the parameters of the language model, and then optimize these, vectors over here. And because of that, it's easy to optimize, gets good accuracy, and other things like this. So I definitely take a look at this paper as well if you find this interesting. Okay. Normally I would stop for questions here, but just to make sure I get through everything, I'll continue on. But actually, I do see I have one. How do you choose the number of slots allocated for the triggers? Are all the generated prompts non-natural, even in the case where a natural solution exists? Why are the generated prompts not natural? I assume that that's talking about the AutoPrompt thing here. So that's a good question. I think basically the number of slots is a hyperparameter. You just pick the one that gives you the best accuracy. Are all the generated prompts non-natural? So this isn't my work. This is somebody else's work. So I can't say with 100% confidence, but all of the ones they presented in their paper were very unnatural. I think part of the reason why is there's really no constraint that would make them be natural. Still, nonetheless, you might guess that the optimization process might find something natural anyway, but it doesn't seem like that's what ended up happening. Okay, so now I'm going to talk about how can we know when language models know. we have two papers that vary by only one function word in them, which apparently was a little bit tricky, and we might have made a mistake on this. But this is a completely different paper that just came out very recently, Tackle 2021. And basically, what we're trying to do is we're trying to answer the question of knowing when language models actually know the answer with confidence. And the reason why this is important is because language models are not omnipotent. They've failed to provide appropriate answers in many cases. So this is an example from GPT-3 where it says, how many eyes does a giraffe have? A giraffe has 2 eyes, which is correct. But then we ask, how many eyes does my foot have? And it answers, your foot has 2 eyes. How many eyes does a spider have? A spider has 8 eyes. How many eyes does the sun have? The sun has 1 eye. How many eyes does a blade of grass have? A blade of grass has 1 eye. So obviously, 3 out of the 5 here don't have a good answer, or the answer is 0. It doesn't have any. But nonetheless, the model basically provides an answer. Another really bad example, and also I think this is an example of why we need to be careful before just deploying models, is somebody tried to build a medical chatbot using GPT-3, and then the question was, I feel very bad, should I kill myself? And then GPT-3 answered, I think you should. So obviously, in situations like this, the language model should definitely say, no, I don't know the answer, or I cannot answer that with confidence, or something like that. So our motivation is, how can we know when language models know with confidence the answer to a particular query? And we examine this from the point of view of calibration. So what model calibration means is a well-calibrated model's probability estimates should be well aligned with the actual probability of the answer being correct. So in other words, for correct predictions, we want the probability to be high. And for incorrect predictions, we want the probability to be low. And the reason why this is useful in this case is if we want the model to be able to say, no, I don't know that, then all we need to do is look at the probability of the answer being correct. And if the model is well calibrated, we could say, well, we don't want you to return any answers where you're not more than 50% sure of it being correct, or more than 20% sure of it being correct. Now, to put this a little bit more formally, we can describe it using this equation. And basically, on the right side here, this is saying that the probability of the output is equal to P. And then on the left side, we have the answer is correct. And so basically conditioned on the fact that the model said the probability is P, the probability of the answer being correct is also P. So this is a perfectly calibrated model, because basically if it says the probability of the answer is 50%, then it is actually 50% likely to be correct. So unfortunately, it's not easy to, we'll never have a perfectly calibrated model. So the way we can measure how good the calibration is, or one way we can measure how good the calibration is using a metric called expected calibration error. And the basic idea is that we bucket predictions into equal size bins based on their confidence. And then we take the average of the difference between the accuracy and the confidence for this bin. And to give an example of what this looks like, we have something that we call a reliability diagram here. And the reliability diagram, basically, this is the bin of things with a confidence between 0 and 0.1, 0.1, 0.2, 0.2, 0.3, or actually maybe it's, 0 and 0.05. And for this particular model, regardless of what the model says its confidence is, the accuracy is about 25% of being correct. So even for the ones where the model says it's confident, it's 25%. The ones where the model says it's not confident, it's 25%. So this is a very poorly calibrated model. And a well-calibrated model, on the other hand, would have this sort of shape like this. And the expected calibration error is basically how much does the blue bar diverge from the red line here. So the expected calibration error for this would be low. So we applied this to language model-based question answering. So this is a little bit different than what we did before. Before we were talking about just kind of factual queries about relations, but now we're talking about multiple choice question answering and extractive question answering using all these data sets on the right here. So in multiple choice, we have like 4 candidate answers, for example, and we want to be calculating the probability over these 4 candidate answers. We normalize so that the probability of each answer sums up to 1. And for extractive question answering, basically what we're doing is we are trying to find a span in an input document that answers the question. And the way we can do this is we can basically feed in the input document and the question to the language model and get it to output an output or output an answer. So here are some concrete examples. So in multiple choice, we have oxygen and sugar are the products of A, cell division, B, digestion, C, photosynthesis, D, respiration. And so the candidate answers are these, and then we hope that it picks photosynthesis. And then for extractive QA, we have what type of person cannot be attributed civil disobedience. And then we have kind of a definition or a document, and we hope the model outputs head of government. So the first contribution of this paper is just to measure the model calibration over a variety of different models, including T5 Unified QA, which is a version of this larger T5 encoder decoder model that was specifically trained for question answering. Also BART and GPT-2. But the second the second contribution of this paper is basically that we proposed a number of methods to increase or improve the calibration of models. And we did this through 3 different kind of varieties of methods, each of which had 2 sub methods. So the first one is fine-tuning based methods, where we actually try to fine-tune the model to achieve better calibration on the tasks it's being tested on. We also have post-hoc calibration, where basically we do a temperature-based scaling or train a decision tree. And then we also have LM-specific augmentation methods that do candidate answer paraphrasing or input question augmentation. And I'll talk about each of these in turn. So for fine-tuning based methods, basically what we did was we only considered candidates in the candidate set. So for example, if we're doing multiple choice questions, we have 4 candidates in the candidate set. So what we do is, instead of training the model directly to be a language model, we train the model to be good at answering these multiple choice questions with the appropriate level of confidence. So we fine-tune the language model to try to like maximize the probability here. We also did a margin-based method because in the past we've found that margin-based methods tend to do a little bit better at optimizing these sorts of kind of multiple choice question answering tasks. So we also tried this as well. So post-hoc, in contrast to the previous things where we're actually training the model to do better, post-hoc calibration methods keep the model as is, but they manipulate the confidence of the model. in some way. So basically, we take the model and we get its log probability. But before we calculate the final probability, we divide it by a temperature, or sorry, this temperature-based scaling method is this type of method. So we take the output log probability, divide it by a temperature, and renormalize. And so if we set this this temperature to 0, that means we'll increase the confidence by infinitely. So we'll put all the probability on the highest scoring output. And if we set this temperature to infinity, it would make the confidence very flat. Or every output would basically get the same probability. And then this is a hyperparameter that we want to adjust to make the confidences more peaky or more flat. We also tried a method where we take a decision tree, where we train the decision tree to try to predict the actual confidence given some input confidences. So in this case, we have the language model probability, the entropy over the output, a language model probability of the input, which kind of tells you how likely you think the input is, or how comfortable the model is with the input. Also the length and other things like this. So the idea being that if we take in all of these features, we might be able to output a better estimate of confidence. Also, because we're specifically talking about language modeling, there's some things that we can do with respect to language modeling. So one of the ones is we tried paraphrasing the candidate answer. And so here we have like excited, careless, and devoted. But maybe the language model doesn't really know the word devoted very well, but if it had the word dedicated, it would be able to answer the question more with more confidence. So basically what we did was we paraphrased all of these answers in a similar method that we used before. And so now the probability of devoted is the sum of the probabilities of all of these paraphrases. Another thing that we tried was we did input question augmentation. So basically, we just tried to gather more evidence from Wikipedia to try to answer the question. And the motivation behind testing this method is we'd like to know, essentially, is the model able to better know what it knows or doesn't know? Is the model able to better predict what it knows or doesn't know if it's given more evidence upon which to base its decision? And this can also increase accuracy overall as well. So it's not just with respect to calibration. So we tested this on several different data sets. One is on a multiple choice QA data set. This is in distributions for the unified QA model. So the unified QA model has actually been trained on the training set of these data sets. We also have another one, MT test, which is a multiple choice QA data set based on kind of common sense knowledge that was particularly hard. It's also out of distribution, so the model has not been trained on this data. And then we also have a few extractive QA data sets. And we measured expected calibration error and accuracy. And so what we can see is basically we tested the T5 model and the unified QA model. And actually, the unified QA model had relatively good, reasonable calibration on the data sets that it was tested on, and reasonably good accuracy, like 76.9%. However, on the data set, on the multiple choice data set that it was not tested on, it had a relatively large expected calibration error of 22%. So basically, this is kind of an important result, I feel, also because it shows that when you move out of distribution, your model is less good at knowing when it knows or doesn't know the answer. So we also tried some tuning methods that either use softmax or margin-based tuning to try to improve the performance on these data sets, and we found that this helped quite a bit, reducing the expected calibration error by quite a bit while not hurting the performance too much. And then we also applied all of the post-hoc methods that we talked about, and we could see that in the end, we were able to reduce the expected calibration error from like from 9.5% to 4.4%, or 22.2% to 7.5%. On the extractive data sets, the result was a little bit less stark, but we still see some degree of improvement. Here are the reliability diagrams that I talked about before. So we can see that before this sort of calibration or improvements of calibration, both of the models, particularly the T5 model, but also the unified QA model to some extent, were overconfident at low probability areas and underconfident at high probability, or sorry, overconfident when the probability was high and underconfident when the probability was low. So basically, we can see that after all of the tuning methods, we get a much nicer reliability diagram here. And also importantly, the confidence kind of varies across different questions. So it's not always saying I'm 100% certain or I'm not very certain at all, but it's rather spreading the confidence out. So you have a good estimate. We also tried this on different LMs. I'm running out of time, so maybe I'll skip this. But basically, long story short, this works on other LMs as well, and for different sized LMs as well. Larger LMs tend to be better calibrated in the first place, but the methods we propose still seem to work okay. So that's all I had for today. And the conclusion was that prompts allow the use of language models as few-shot learners. So we can take language models and ask them to solve different varieties of tasks. And how can we know what language models know? We could do that through better prompt design using either the methods I presented or some other newer methods like the ones I talked about. And how can we know when language models know? We can do this through calibration. And these papers both have a lot of additional detail that I didn't have time to talk about here. So if this sounds interesting to you, I'd encourage you to take a look at it. Thanks. That's all I have for today.
All right, so thank you again, Graham. I think that you already answered to a lot of questions. So I don't know if anyone has more questions or not.
I have a small question to boost up the questions. So regarding the optimization of the ensemble weights for the first paper, it assumes that the LMs know the gold factual queries that are used to optimize. So what happens if the language models don't know those queries? Like, what are you optimizing then in the optimization of the ensemble weight?
So in all cases, the model is predicting over the entire vocabulary. So because the model is predicting over the entire vocabulary and it will assign at least some probability to the correct answer, you're basically just optimizing the probability of the correct answer, even if it has no chance of ever getting it right. Not because it's because it's not within the oracle.
Yeah, and I guess this ties with my next question, which is like we're optimizing for prompts for maximizing, like the question is optimizing prompts really measuring what models know? Because my intuition is that measuring what models know should be the expected value over prompts that are semantically equivalent, and should be the expected value over prompts, not the prompt that maximizes the accuracy. It's just like a more general argument. Like, is using the prompt the most optimal prompts to get the right answer, knowing what the model knows, or should that be the expected value over the prompts that ask the same question?
So that's a good question. The way we defined it was essentially more like the expected value, or I guess weighted average. And if the best scoring thing with the weighted average gave you better accuracy, we said that.
But then the expected value for the weights were calculated to maximize what the model knows in some sense. So this is more like, obviously the answer is not trivial. It's just what made the intuition be that to know what the model knows should be the prompts that maximize this goal labels on the training set, rather than some other distribution of a prompt, let's say.
So that's a good question. And actually, what I said at the beginning is that we were just trying to get the best lower bound.
Yeah.
And so the way we get the best lower bound is we try to improve our accuracy as much as possible. And there certainly is a possibility that you could do more.
Okay, thanks. There are some other questions now as well.
Yeah. Okay, great. I saw one in the chat first, and then I'll get to the ones in the QA. So I got, can we put calibration, the second part, and prompt ensemble together to get close to Oracle performance? That's a great question. That we didn't try to do that, but if you, yeah, I imagine that would probably improve the accuracy, but we didn't try it, so I don't know. I don't know. Cool. And then language models seem to have lots of information and are very good at low level, but not real high level logical thoughts. Do I think that we can achieve high level directly through deep neural models, or do I think we need to include a reasoning system more similar to have a high level processing system come out of these models? So that's an excellent question. And my answer to this is, in theory, neural networks should be able to do anything. So it's like they have the computational power to answer, any sort of high level question that we would like. You can actually prove that. There's a paper like transformers are universal approximators of sequence-to-sequence functions, which means that they should be able to model any function we would like to model. Then the other question is, would we ever actually learn that from data? And the answer to me now seems like at least some variety of reasoning is happening within these models. Like, if you look really closely at the answers they're providing, you wrote down the logical steps that you would need to know in order to get there. I think in many cases, it would certainly be more than one logical step to be able to answer that question correctly. However, most of the time they, or much of the time they fail at doing this. And there's plenty of examples from the Mina chatbot that I kind of showed before, where it's just like, for example, it's not remembering the information or it's not acting like it remembered the information it had been told before. So I think there's a number of ways that you could tackle this. One way you could tackle this is by coming up with a better model that has some sort of like explicit symbolic reasoning component incorporated in it. Another way you could do this is you could try to essentially generate data for the language model where it would be necessary to do the symbolic reasoning in order to predict the correct answer, and just generate lots and lots of this data to encourage the model to, learn this capacity. I think part of the reason why it becomes hard to do these more complicated things with language models is just because despite the fact that their training data is huge, most of the time they don't need to do this sort of reasoning in order to predict the next word successfully. So yeah, it's a very good question. I don't think anybody knows the answer to it right now, but hopefully we will in a few years. So In the ECE formula, is it compulsory to use accuracy as opposed to precision recall or F1 score? How much can calibration be distinguished from re-ranking? It is kind of compulsory to use accuracy, I think, because this is the definition. This is the definition of kind of calibration, I guess. So you might be able to come up with analogous ideas, but if we're talking about pure calibration, I think it would be accuracy. How much can calibration be distinguished from re-ranking? I think they're kind of distinct concepts, but maybe if you're talking about the methods that we used, you could also think of some of them as re-ranking. This method here will never change the ranking of any of the outputs. This temperature-based scaling method, the ranking will be exactly the same regardless of the scaling you use. But any of the other methods could change the rank of the outputs because you're training the model or you're learning new confidences. So those could be, could result in re-ranking. So what is the link to the paper to read more on it? So both of the links are on my website. So maybe you could go to the publications page and search for language models no, and you should be able to find both of them. Also, I did send the slides to the organizers, so maybe they could distribute them and you could find them there as well.
Yeah, the slides will be put on the webpage, so
okay.
You can also look from there.
Great. And confidence shouldn't change inference much. In the case of temperature variation tuning, it doesn't change the max value, which shouldn't prevent the model from predicting you should commit suicide. Yeah, so basically the idea behind calibration is you would like to know how confident the model is, and then you can add a post-hoc filtering thing that basically says the model is not confident enough to provide an answer in this particular case. I think that would be, well, you could hard code, I don't know, or something like that is the response as well. Great. Yeah, thank you so much for all the questions. That was a great number of interesting questions. I'm happy to discuss them. It looks like maybe we're done.
Yeah, I think so. So thank you again, Ron. So for today, this was the last talk, and tomorrow will be a free day to recharge some batteries, and on Monday we'll get back. Bye.
Thank you, Graham, for the great talk. Bye-bye.
Thank you very much. Bye.